In physics, unification refers to the attempt to describe all fundamental forces within a single theoretical framework. The electromagnetic, gravitational, strong nuclear and weak nuclear forces are the four fundamental interactions currently known. Unification seeks to explain these forces as different aspects of a single, more fundamental force. Historically, scientists such as James Clerk Maxwell unified electricity and magnetism into electromagnetism, and Albert Einstein attempted to unify gravity with electromagnetism. The ongoing search for a unified theory continues to be a central goal in modern physics. The four fundamental forces in nature are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the force of attraction between objects with mass. Electromagnetism is the force between electrically charged particles responsible for electric and magnetic fields. The strong nuclear force binds protons and neutrons together within atomic nuclei. The weak nuclear force is responsible for processes such as radioactive decay and neutrino interactions. These four forces define all known physical interactions in the universe. In the 17th century, Isaac Newton formulated the law of universal gravitation, demonstrating that the same force governs both the falling of an apple and the motion of the moon around Earth. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single framework, electromagnetism, showing that light is an electromagnetic wave. Maxwell's equations established that phenomena such as lightning and radio waves are manifestations of the same fundamental force. In the early 20th century, Albert Einstein developed the theory of general relativity, providing a new understanding of gravity as the curvature of spacetime. Einstein also sought to unify gravity with electromagnetism, laying the groundwork for future research in unification. These scientific milestones mark the foundational steps in the ongoing pursuit to unify the fundamental forces of nature. In the 20th century, physicists identified the strong nuclear force and the weak nuclear force as fundamental interactions, in addition to electromagnetism. The strong force binds protons and neutrons within atomic nuclei, while the weak force is responsible for processes such as beta decay. In the 1960s, Sheldon Glashow, Abdus Salam and Steven Weinberg developed a unified theory of electromagnetism and the weak force, known as the electroweak theory. The electroweak theory was experimentally confirmed at CERN through the discovery of the W and Z bosons. These developments form the basis of the Standard Model of particle physics. The Standard Model describes three fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It also classifies all known elementary particles including quarks, leptons, and gauge bosons. The Standard Model has been extensively tested and its predictions have been confirmed with high precision. However, the Standard Model does not incorporate gravity. Gravity is described separately by Einstein's general theory of relativity. The Standard Model operates within the framework of quantum field theory. Currently, there is no experimentally verified theory that unifies gravity with the other three fundamental forces. The unification of gravity with the electro-weak and strong forces remains an open problem in physics. Research continues to seek a comprehensive theory that includes all four fundamental forces. The goal of a theory of everything is to create a single framework that unites all four fundamental forces of nature. Grand unified theories propose that at extremely high energies, the strong nuclear force merges with the electro-weak force, suggesting a single force existed in the early universe. String theory is a leading candidate for unification. It describes all particles as tiny vibrating strings, with different vibrations corresponding to different particles and forces, including gravity. String theory requires additional spatial dimensions beyond the familiar three, but these extra dimensions have not been observed, and the theory remains untested experimentally. Currently, no theory of everything has been confirmed, and the unification of gravity with the other forces remains an open problem in physics. Research continues as physicists test new ideas and search for experimental evidence that could support or refute these theories. The search for a theory of everything is ongoing with no definitive solution yet achieved.